In the last video, I concluded by saying that waves were an example of harmonic motion where particles are sort of repeating their path, which is the definition of harmonic motion. And so from a wave, you might not really see, how is a wave repeating its actual path. Well, if we look at this example right here, this shows a wave, and you can see that the actual particles of the wave are not moving across the screen. The wave itself is moving, but it's really just a transfer of energy. The particles that make up the wave are oscillating or repeating their path. So if we look at this particle, if we imagine this thing as a slinky, the matter of the slinky is just going up and down in this periodic motion. So that's why waves are considered oscillating or harmonic oscillators. So waves are oscillating disturbances. And if we look here, this is an example of a water wave. We also look here, you can see the example of maybe a string vibrating on the end of a blade. So you can see that as the string vibrates, the string isn't actually moving left to right. The wave moves left to right, but the particles of the string do not move. They are actually moving perpendicular to the wave motion. So I'm going to kind of define the different kinds of waves in this lecture, and then we'll move on to wave structure and then specific types of waves later. So mechanical waves are a wave that need to transfer through a substance. And again, like I said, the particles are not moving in one direction, it's actually a transfer of energy. So a mechanical wave is a transfer of energy through a substance. So they require some sort of medium. So for example, there's the idea of earthquakes and tsunamis. So in these instances, an earthquake's medium is the ground, so it's a solid medium, whereas a tsunami, the example would be a liquid medium. Now, sound is also an example of a mechanical wave, and in this case, the sound is actually air particles, right? So air particles that are coming in contact with each other and colliding with each other and transferring the energy. So they do require some sort of medium. Now, if we look at here and we think about how quickly does a mechanical wave travel, most people think, well, a mechanical wave would travel fast in sound because air seems less dense, so the wave could travel through. But that's using the false misconception that waves are actually particles moving through space trying to sort of navigate around things. But essentially all it is a transfer of energy, two particles running into one another. So the closer the particles are to one another, the more quickly they're going to transmit that energy from one particle to the next. So because particles of a solid are very close together, the mechanical wave actually transfers the energy a lot quicker in solids and liquids than it does in a gas where the particles are very spread out from one another. Now, one thing to keep in mind is we're going to look at these waves as if they sort of move in one direction, left to right, because we're looking at the wave energy moving in a specific path. But all mechanical waves are actually circular waves. So there is a point of propagation and they radiate out from that point. So just keep that in mind as we now start to look at waves as more of a linear thing in order to understand them a little bit better. Mechanical waves, such as sound waves, are longitudinal waves. So this is also called a compressional wave. So you can see the compressional wave being propagated here on this slinky. So if I were to push the end of the slinky, it travels in this direction, and a compressional wave actually has particles that travel parallel to the direction of the wave velocity. So the wave is going left to right, but also the particles are going left to right, which is a little bit different than the examples that we saw for the harmonic oscillator example at the very front, and when we look at the the string on the blade. But all sound waves are actually compressional waves, where the particle motion is parallel to the wave travel. Now, we also have another type of wave that's not a mechanical wave, and this is the idea of electromagnetic radiation. Okay, so electromagnetic waves are also called radiation, and we receive much of the radiation that we experience from the sun. And they all move at the same speed, which is c, the speed of light, 3 times 10 to the 8th meters per second. And that will come back to be important later as we actually start performing some calculations. Now, electromagnetic waves are actually transverse waves, and they're actually perpendicular to one another. A electric field and a magnetic field running perpendicular to one another. And there are all sorts of different kinds of electromagnetic waves, and based on their size, we give them a different name. So there's visible light that we can see, but all of these are exactly the same type of wave. They're just given a different name based on their size. So UV, X-ray, infrared. And again, we'll go into more detail when we start talking about light or electromagnetic waves in topic 3. Now, these waves, unlike sound waves that are compressional or longitudinal, are transverse waves. And in this case, the particles are going to be moving perpendicular to wave travel. Okay, so those are some definitions into the different types of waves that we'll be looking at throughout this unit.